Yet another colligative property is osmotic pressure. So, osmosis is the flow of a solvent from a solution of low concentration to one of high concentration. And this happens across a semi-permeable membrane. So right here, here's our semi-permeable membrane right there. And that's going to allow solvent particles through, but not solute. And our cell walls are a semi-permeable membrane, and it's made with a lipid bilayer. And so we can easily get small nonpolar compounds across through the nonpolar middle part of our bilipid layer. And we can get water across, but we couldn't get like ions to pass across the semi-permeable membrane without an actual ion channel to shuttle them through. So when we have a semi-permeable membrane, we see that if we have a solution, and let's just take salt water for an example, on one side and fresh water on the other, like we have here, that driving force to mix will drive the water across the semi-permeable membrane, the solvent, to try to dilute the more concentrated side. And so we see water actually flow across the membrane, and we see our less concentrated solution, our pure water in this case, that volume decrease as we increase the volume in our more concentrated water because we're trying to the water is diluting that solution by passing across the semi-permeable membrane. And this is osmosis, this drive for water to flow across that membrane to the more concentrated side. And I had a student come up with a fantastic way to remember this. Water always goes to the party, or water is always following the party. Like it's always going to move in the direction that there are more particles. Now, at some point, as those water molecules travel across the semi-permeable membrane and we see this change in our volumes, there's going to hit a point where enough water has traveled into the more concentrated side that the volume is significantly higher and pressure builds up of that excess fluid, with the atmosphere pressing down and just gravity itself, and we'll stop seeing that flow of water. And so when we see that flow stop, we characterize that by osmotic pressure. So it's the amount of pressure that's needed to actually keep the osmotic flow from taking place is what we consider osmotic pressure. So osmosis is the flow of the water through. Osmotic pressure is how much pressure does it take? How much force do I have to press down on, I guess, my more concentrated side that would prevent the water from flowing across the semi-permeable membrane. And we characterize this with an equation that is reminiscent of the ideal gas law. Got it right here. So osmotic pressure is this like capital pi sign, and it's times the Van Hoff factor again. So we know how many of our particles we have. This large M is molarity this time, so moles per liter. R is our gas constant, and we're going to use the version of our gas constant that has atmospheres in it. So that's 0.0821 liters times atmospheres divided by moles Kelvin. And we have temperature, which will always be in Kelvin. So we don't have a zero that we're multiplying everything by. So this number we can calculate for osmotic pressure will be the pressure of the excess fluid that would prevent that flow. So if I wanted to calculate this by way of example for sodium chloride, a saline solution at room temperature, I would have that sample down here. So I would use my actual Van Hoff factor. Now the theoretical one is 2. And so I'll let you know in a problem if you need to use the theoretical one, which most commonly will do, or the actual. Our concentration for our saline solution is 0.154 molar. Then we use our R constant. And if we do this at room temperature, it'll be 25 degrees Celsius, which would be 298 Kelvin. And just calculating all that together, I get a osmotic pressure of 7.16 atmospheres for just a saline solution level of concentration for our sodium chloride. Let's look at this in the body. So we have a lot of semi-permeable membranes in our bodies. So they make up cell walls, these bilipid layers. And so we can have intracellular fluid, which is going to be fluid that's inside of a cell, and extracellular fluid, which will be outside of the cell. And if the concentration is different on opposite sides of this cell wall, we'll see water travel across the cell wall, either into the cell or out of the cell. And this is where we come up with the terminology isotonic, hypotonic, and hypertonic. So isotonic is going to mean the same pressure as the body. So it's saying that the concentration of a fluid, if it's isotonic, is going to have the same concentration of solute particles as you would find inside a cell. So that's going to be different depending on the number of particles that you have from your compound. That's going to look like about 0.92% by mass volume of sodium chloride. And this is similar then if we change this into molarity, it's about 0.154 molar or 5% mass per volume of glucose. Now, if I have a hypertonic solution, then it means that the solution surrounding the cell is actually at a higher concentration than the fluid inside the cell. So it has a higher osmotic pressure than the body. And that means that water is going to diffuse out of the cell. We're going to see it leave, and that cell is going to crenate. It's going to shrivel up and start to look pretty sad. If it's a hypotonic solution, then what we have is a solution surrounding the cell that is at a lower concentration, which means it'll be at a lower osmotic pressure than the body. And so what happens then is, remember, water's going to follow the party. So water's going to flow into the cell to try to dilute it. And that's going to have water diffuse into the cell and expand it until it bursts. So hypotonic solutions, if they're hypotonic enough, will lead to the cell expanding and bursting. Hypertonic solutions, if they're concentrated enough, will shrivel cells up.